Is that
good afternoon, everybody. Can everybody hear me?
Yes.
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 Just making sure the equipment is.
Hi, Paolo.
Hello.
You?
So what's the weather like in San Francisco, Valeri?
It's hot here. I wish it was. No, I'm still in the UK. It's just all right. So shall we start? We have, I think, time. So first of all, thank you to the organizers for inviting me to chair this tutorial. And just to say a few words about conformal predictive distributions. As somebody who has done research in this area, and we published, I think one if not the first papers, kind of using data-driven approaches to what was previously known statistical predictive distributions, right? Using the parametric forms. I think this is a very, very exciting branch of conformal prediction. And it's good to see there is a lot of papers recently on this topic. Without much ado, I would like to introduce Paolo Toccaceli, who is a researcher in the Central for Reliable Machine Learning at Rowe Holloway. Paolo has been successfully applying conformal and probabilistic techniques to complex real-world problems, including in the domain of chemoinformatics, and we saw he also has shared kindly for the community some libraries, including on Venn-Numbers predictors and things like this. So very much looking forward to hear this talk. This is a new talk as well, and over to you, Paolo. Thank you.
Thank you for the introduction, Valeri. In the tradition of the presenters that preceded me, I will start with a disclaimer. The presentation that you're going to see is intended for students. Therefore, it tries to focus more on the concept behind it and sort of dispenses with rigor in some cases. But I hope you will find useful anyway. So let's start with what conformal predictive distributions are. They are a novel approach to estimating the probability distribution of a continuous variable that depends on a number of features. So you could view it as a form of regression plus probability. As Valeri just mentioned, they are a new development. Professor Vovken and others published in 2017, as far as I know, the first paper on conformal predictive distributions. The key property of conformal predictive distribution is that the probabilities that they output correspond to long-term relative frequencies within statistical fluctuation, and they do so under minimal assumptions. So they require only that the data be generated independently by an unknown but fixed distribution. So there is no assumption on the type of distribution, and there's no need of a prior. The tutorial is broadly articulated into 4 sections. The first one where I give some context and motivation, then a second section in which I define our meaning here of predictive distribution, and I introduce conformal predictive distributions. And then in a third section, I talk about a specific case of conformal predictive distribution, which is called the kernel ridge regression predictive machine. And the tutorial ends with an evaluation of techniques for evaluating predictive distributions applied to some real-life examples. So let me start by giving some sort of a historical context. Statisticians started investigating a similar problem, not exactly the one that we are addressing with predictive distribution. And the problem was one of parametric inference. So suppose we have data D generated by a known distribution with a known parameter theta, which we want to estimate. Bayesian statistics very naturally can estimate a probability distribution for the parameter. And they do so by applying fundamentally Bayes' theorem. So as you see in the slide. But the problem with that is that you have to specify a prior distribution for the parameter. Frequentist statistics cannot do what Bayesian statistics can do, but instead provides confidence intervals. So you choose a coverage probability alpha between 0 and 1, and then you can compute an interval by means of 2 functions, L and U. And this interval contains the actual theta, a fraction alpha of the time as you sample the data D. It is important to notice that in a strict frequentist framework, you cannot even talk about the probability distribution of theta given the data, because theta is a parameter, is a state of nature, and it's a tenet of frequentist statistics that you cannot assign a probability to a state of nature. It is out there. The gravitational constant is out there. It doesn't have a probability of being within a certain interval. However, frequentists recognized that a similar concept would be to a predictive distribution would be very useful. And it is so useful that recently some statisticians defined the problem of prior 3 posterior distributions as the holy grail of parametric statistics. And there were early attempts, as early as the 1930s, with Fisher's fiducial approach. The problem with Fisher's fiducial approach was that it wasn't completely formalized. It was worked mainly through examples. It ended up being very controversial, and by some detractor, it was referred to as Fisher's biggest blunder. Now there is a resurgence of interest in the topic, and what I'm going to show for conformal predictive distributions is part of this trend. So let me try to provide a definition for predictive distribution, which might not be the same as you would see perhaps in a Bayesian context. So we're going to operate in a regime of unrestricted randomness with IID data. So we have a data set composed of observations, each made up of an object X with features and a label Y, which depends on the features. And we assume that this data set is generated independently by a fixed but unknown probability distribution. In intuitive terms, we seek a function f of y and x given the data set D that has the properties of a cumulative distribution function. So we want a function that expresses the probability that the random variable y be less than a given value, lowercase y, given that the random variable x takes the value lowercase x. So in other words, and more specifically, as long as the test points come from the distribution, the same distribution from which we've drawn the training data, the intervals minus infinite y contain the actual label yi with relative frequency given by the function f and evaluated in y and xi. Before I provide the definition of conformal predictive distribution, I want to remind you of the property of cumulative distribution function. So if we have a random variable x, and we denote with f with x the cumulative distribution function, and the expression of the cumulative distribution function, then there is this property that if I take instances of the random variable x and I evaluate the expression of f with x on these variates, I obtain numbers that, of course, are between 0 and 1, but that are uniformly distributed. This can be proved for a continuous cumulative distribution function, but also we can relax that condition, and we have to change a little bit the sense in which this is true. But this is important to understand and accept the definition that I'm going to show in a moment. So let's define predictive distributions for our context. So we have observations Z1 to Zn from a set Z, and a test object denoted with x with n+1. So we call predictive distribution here a function Q of the training set Z1 to Zn and of a hypothetical test observation made up of the test object and our hypothetical value for the label that has the following properties. For any choice of training sequence and any choice of test object, Q has the properties of a CDF. So it's monotonically increasing in y. Its limit for y that goes to minus infinite is 0, and the limit for y that tends to plus infinite is 1. And for any joint probability P on Z, the values of Q is evaluated on Z1 to Zn+1 are uniformly distributed when I draw Zn and to Zn+1 IID from P. And I hope that you can now accept this last statement as something that gives the properties of a CDF based on what we just said. To be perfectly honest, this definition omits some technicalities that we'll talk about later. So the key property of predictive distributions, as I mentioned at the very start, is the fact that they have guaranteed, that they can produce intervals with guaranteed coverage. And the guaranteed coverage is a consequence of the uniformity property. The guaranteed coverage consists in this, and I'll try to explain this first with an example. If we look at the chart in which I depicted a hypothetical predictive distribution for a hypothetical test object X. If you consider the value of cumulative probability 0.6 on the vertical axis, the dashed line intercepts on the graph of the cumulative of the predictive distribution a point with a coordinate 0.79 on the horizontal axis, which is the axis of the label y. So what we are saying is, if I construct intervals in this way by taking the graph of the predictive distribution and finding the point for y that is intercepted by the value of the vertical axis 0.6, if I repeat this for all the test objects, I obtain intervals such that the frequency with which the actual variable is less than the prescribed value for y is 0.6. This is the meaning of guaranteed coverage. It is sort of the operational meaning, if you will, of guaranteed coverage. And given that I have this, I can now talk about intervals. I can take an interval like I'm showing here with width 0.2, and this identifies an interval of y values that has the property that I was mentioning before of coverage. Differently from the intervals that are generated with the procedures that I mentioned before, we can choose a variety of prediction intervals. It's just a matter of setting a strip, for instance, of width 0.2, as illustrated here, and you can shift it up and down the vertical axis and identify intervals for the label y with the desired property of coverage. One desirable thing to do is to choose the positioning of this interval such that we have the narrowest y interval, because we want predictions to be as concentrated as possible in a as narrow as possible interval for y. And you do that by looking for the slope where the predictive, the part of the graph where the slope for the predictive distribution is higher, has a higher slope. But another method for choosing an interval might as well be one of choosing it symmetrically around the median, as I did in a previous slide. So generally, when I talk about CDF, I get sort of perplexed looks by practitioners, because people tend to be looking for or expect a probability density function. But I will give you a little bit of a sales pitch for cumulative distribution functions. The first thing is that there are theoretical results guarantee that the ECDF converges to the CDF for IID data. And this is called the Glivenko-Cantelli theorem, and it's a fundamental result in statistics. And then there's the other fact that the ECDF converges fast to the ECDF being the empirical cumulative distribution functions that we can obtain for data, because the only thing that we see from reality is data. We are not seeing distributions. The ECDF converges fast to the cumulative distribution function, and this is ensured by the Dvoretzky-Kiefer-Wolfowitz inequality. And then the problem is that you could view the probability density function as a sort of derived notion that you can obtain by solving an ill-posed problem. And one way of stating the problem is by means of this integral equation that is known as a Fredholm equation of the first kind. And the problem that is that this formulation or other equivalent formulations are not stable. And the stability is a property that ensures that a small variation in the right-hand side, capital F of X, which is what we can obtain as ECDF, results in small changes in the solution. And unfortunately, this is not true. And when you have this sort of problem, then you have to contend with an extra layer of complexity and use methods that are specialized for this sort of problem that employ things like Tikhonov regularization. So these are sort of theoretical considerations. They might leave you cold, but let me give you some other practical perspective, perhaps. I think there are pros and cons with using CDF. Computing in a CDF is an empirical cumulative distribution function from data is straightforward. And the other thing is that you can read probabilities easily off the chart. Whereas you don't quite can do the same thing on a PDF chart, unless you know how to integrate by site, and it's not something I can do. However, there are also some cons. The fact is that if you're interested in rapidly identify the modes, so the values with highest probability density, this is rather difficult from the CDF because there is a perceptual problem of evaluating the steepness of the slope. And that's a limitation, but somehow I feel that CDFs are more honest, and people tend to misinterpret probability density as probability, whereas it's not. So probably in my experience with communicating this with non-experts, that this can be a problem. So now we are in a position to talk about conformal predictive distributions. And this is a general framework that allows us to obtain predictive distribution using a variant of conformal prediction for regression. So we are using, basically, we have a method set that can use an underlying regression algorithm, provided that it meets some conditions that I'll talk about in the next slide, to obtain a distribution out that has the property of validity, of guaranteed coverage. So now that you're familiar, based on the previous tutorial with conformal prediction, I'm going to show something that it's pretty similar to transductive conformal prediction, but there are some differences later. So again, the key ingredient is a function that we call conformity measure, which is a function of n+1 observations and is invariant with respect to permutations of the first n arguments. You can think of this as a way of expressing the conformity of the n+1 argument, so the n+1 observation, given the previous n observations that come from our training set. So given a hypothetical observation made up of our test object and a hypothetical label, we compute conformity scores alphas by using basically the transductive approach. So the ith alpha is computed by taking the ith observation that now use as the test observation and replacing in its place the hypothetical. So the We are basically retraining our underlying algorithm with a new training set in which I replaced the test observation in place of the ith element. And I obtain n+1 alphas. So subject to some conditions on the function capital A, the predictive distribution is given simply by counting the alphas that are less than the alpha of the n+1, corresponding to the n+1 element, and dividing this by n+1. So it's a, you could view it as some people observed before as sort of a rank statistics. So the requirements on the conformity measure, as I mentioned, not all conformity measures lead to valid predictive distributions. And this is a difference with respect to conformal prediction. So first of all, an observation. You could view Q as the estimate of probability under IID of drawing an observation with a smaller value of the conformity measure than the hypothetical observation made up of the test object and the value y. And in a way, it is as if we were testing the null hypothesis of IID using alpha as a test statistic and computing a p-value by means of Q. So there is some sort of connection with statistical hypothesis testing, if you will. Now, let me say something about the additional requirement on the function A. The function capital A that I mentioned before must be such that the alphas have these properties. The difference between the alpha with y and n+1 minus alpha of y and I is a monotonically increasing function of y for all values in R, the real axis. And the limits of this difference for y that tends to plus infinite and minus infinite are respectively plus infinite and minus infinite. Not all choices for capital A result in these properties. One very simple case in which this happens is when I define as function capital A the difference between y and y hat with n+1, where y hat is the estimate obtained with k nearest neighbor regression. So as I said before, I took a shortcut. And what I didn't mention before is that in order to define a conformal probability distribution with the rigor that allows us to obtain theoretical results to corroborate our statements, it is necessary to introduce a randomness element. So as you see on the screen here, the first, the function Q is defined as before, but then we add another term which counts the ties, so to say. So the number of cases in which we have the same value for alpha. And it multiplies this by a random variable tau distributed uniformly between 0 and 1. So what we end up having is informally a thick distribution function made up of a number of n+1 steps, each with thickness 1 over n+1. The fact that this is thick is obviously important from a formal standpoint, but in practice, it matters relatively little, because hopefully you're going to have a reasonably sized training set. And of course, as you have a reasonably sized training set, the width is small, especially compared to the kind of errors that you're going to have for other reasons. So up to now, I defined what predictive distributions are. I gave an example of, we talked about the framework of conformal predictive distribution, but I haven't said anything about how to go constructing one, really. So let's consider now the method of kernel-ridge regression predictive machine. And as a regression algorithm, we use kernel-ridge regression, which is a nice method to use because it has two interesting features, so to say. One is the fact that it's a regularized method. So it allows to get the right trade-off in between bias and variance, or between overfitting and underfitting. And then the other part is that it's a nonlinear method, so it can accommodate nonlinearity in the data, and it does so by using kernels. So the conformity measure, our first attempt, which is simply the discrepancy between the value y hypothetical and the value that we predict for y for the test object x with n+1. It's not a proper conformity measure in the sense that it fails to produce a strictly increasing function in y for high leverage objects. So if you have an x which is sort of out there, and which whose effect on the prediction is sort of excessive, this leads to the properties that I was requiring a few moments ago not being met. So another possibility is to include the test object with the hypothetical label in the training set for the KRR. But even this fails to guarantee a strictly increasing function in y. But we are on the right track. And oops, sorry, let's make it better. So what we have now is that a conformity measure can be obtained by actually scaling the difference between the hypothetical object and the hypothetical label and the actual and the predicted label using the method that I used before, if we divide it by an appropriate factor, or you multiply by the appropriate factor. And here we have to take the square root of 1 minus h bar of n+1, which where h bar is the n+1 diagonal element of the hat matrix, which is the hat matrix is what puts the hat on the y values, so makes predictions out of the y values. And its form, its expression is shown here. But you don't have to worry too much about these details. The interesting thing is that there is an explicit form for computing the distribution. So the steps in the distributions that I showed before. And secondly, this explicit form lends itself to be implemented in a way that avoids recomputing from scratch everything. And and the hat matrix in particular for every test object. And the hat matrix is a bit compute intensive because it entails, as you can see here, a matrix inversion. So let's now take a look at what KRRPM as a form of predictive distribution can give you. And I'm taking this example from a study that was part of a collaboration with a major pharmaceutical company, where we were trying to predict the biological activity of a number of compounds on a specific enzyme of interest. And we were given a data set with 1,368 compounds. Each compound was described by 68 features that were physicochemical properties. Out of this set, we extracted randomly a set with 1,000 observations, and we applied KRPM. And what you see in the graph here is a set of predictive distributions for probably 20 or so test objects, each denoted by a different color. And at the horizontal axis is the activity, which is what we want to predict. And this is and you can see the shape of the CDF for or rather the predictive distribution for the specific compound. You can see that the various conformal predictive distributions have different slopes, which indicates that we can predict with different uncertainty the activity for different compounds. Yeah, the vast majority perhaps look like shifted copies of a similar predictive distribution. But again, I want to keep in mind that humans have a difficult perceptual difficulty in evaluating slopes. So there are some clear cases of different slopes, but even when they look similar, there are in fact differences that are sizable. The black dots here are the actual values of the activity. And as you can see, they appear to be uniformly distributed on the vertical axis. And this is precisely what the property I was talking about before refers to. And it's sort of counterintuitive to see this, at least to me, the first time I saw it was counterintuitive that the actual values would be distributed. But it's one thing that from a diagnostic standpoint, diagnostic meaning, are we implementing things correctly, confirms that we're doing the right thing. Okay, so after looking at predictive distributions, at an example of them, we can talk about what desirable properties predictive distributions, as we define them, should have. One we could refer to as validity or guaranteed coverage. So the predicted probabilities for intervals correspond to long-term relative frequencies. And of course, this is to be toned down by saying that this is within statistical fluctuation. But this is for conformal predictive distribution, this is assured as long as the IID assumption is verified. Then the other desirable property is specificity or also sharpness. The intervals for the given probability are as narrow as possible. And the two properties go hand in hand. You can always make a valid predictive distribution. You just output for all the test objects the same predictive distribution, the ECDF of the label. on a training set. However, you immediately realize that this is almost useless forecast. It is as if you went to a meteorologist to ask him if tomorrow it will rain, and he would take the climatological average to answer your question. Of course, this answer would be valid in the long run, as long as we don't have climate change, but it would have no specificity. And you could argue that you can do better, and of course this is true, and of course you can very well imagine that you would lose money if you were to bet using a climatological forecast compared to the forecast with a more skilled forecaster. So the key thing, and sorry if I repeat myself, of conformal predictive distribution is that they guaranteed validity under IID. And the good thing is that you can concentrate on improving specificity. So even if your algorithm is not very good, you still have validity. What you have to do is to improve specificity. And you see this, for instance, when you use the same algorithm and you provide a larger training set, you see the intervals that you obtain becoming narrower and narrower. Their distribution moving towards left in if you do the histogram of the interval widths. So the question that we should pose ourselves now is, how can we say that one predictive distribution is better than another? How do we evaluate them? For predictive distributions, for probabilistic predictions in general, there are some established scores. There's Breyer loss, which is sort of quadratic. There's log loss. And these are used everywhere, if you will. But these apply to tasks in which the predictions must assign probabilities to a set of mutually exclusive discrete outcomes. You can use them on predictive distributions by creating mutually exclusive events, like the value is between these two values or outside these two values. But even, and this is useful, but these do not evaluate the predictive distributions in their entirety. So there has been research in coming up with metrics and diagnostic tools for predictive distributions. And the research was mainly in the meteorological domain, interestingly enough. So I'm going to talk about metrics and diagnostic that have a theoretical underpinning, and they are the probability integral transform and the continuous ranked probability score. But then I'll also talk about more practical ways of looking at predictive distributions, which are the validity plot and the interval box plots. So the first metric that I'm going to talk about is for the purpose of assessing validity. And this is called PIT, or probability integral transform, and has to do with the property that I mentioned before. We evaluate, we take the predictions, which are, in our case, are functions, effectively, in our case are step functions, which should have the properties of cumulative distribution functions. And we evaluate them on the actual label that came up when nature disclosed the label. And as we've seen, if the predictions are ideal, then the values of this Fi on Fy should be variates on the uniform distribution. So what you do then is, generally, it's done in the literature, you plot the histogram of the probability integrals transform, and you verify that it's flat. And if it has deviations, then you know that your predictive distributions are biased somehow. I don't like too much histograms because as a way of estimating density, they are tricky because you have to select the right value for the bin size. Okay, there are other methods like kernel density estimation. Still, you have to choose the bandwidth of the kernel. So as I showed, I would stay away from methods that involve estimating a density if possible. So another way to judge if the PIT is one of a cumulative distribution function is to check that the ECDF, and it should be as close as possible to the 0011 diagonal. And there is also the KS test, which uses a Kolmogorov-Smirnov statistic for this purpose. So getting to the other method that I wanted to talk about, continuous ranked probability score. This looks at probability distribution at the predictive distribution in its entirety. And it can be defined as a quadratic measure of discrepancy between the forecast, CDF, and the ideal forecast, given the scalar observation y. So if we were sure about the value of the label, then we could emit a prediction in which all the probability is concentrated on the value that it takes. So in the chart, I'm showing the case in which the actual y was 0.3. And the ideal prediction that, say, an oracle could give you would be a step function located on 0.3. And what we are doing here is we look at the discrepancy between our forecast and one of the oracle, and we square it and we integrate it over the horizontal axis. For a number of predictions, then one takes the average, and this is what you get out of the CRPS. One interesting thing to notice is that in many cases there isn't a deterministic relation between the features and the label. So the CRPS, even if we were to make the ideal forecast for that particular problem, would have a minimum that would be larger than 0. And you could argue that is the difference between this minimum, between the actual value of the CRPS that you get with your predictions and this minimum that really quantifies the skill of the forecaster or the quality of your predictions. So I'm going to talk now about the practical diagnostic tools, because the problem with the methods that I just talked is that they are theoretically nice, but it's a bit hard to have a direct interpretation, whereas the two diagnostic tools that I'm talking about are direct. And the one I have here is the validity plot. And basically we are showing the actual coverage versus the confidence. We set a confidence level, we compute the intervals for the objects in the validation set. We compute the relative frequency of the event interval contains the actual label, and we plot this value for different values of the confidence of interest. And you obtain a chart where you want your graph to be as close as possible to the dashed line, the diagonal from 0, 0 to 1, 1. This has a very direct interpretation and allows you to see for which values of the confidence you're encountering deviation from validity. Okay, so now the other diagnostic tools that I like to talk about is the interval box plots. And here you look at the sharpness of your predictions. And you compute the intervals, and you basically compute the descriptive statistics of the intervals. You get the median, you get the first 25th quantile, the 75th quantile, and this is what basically the box plots represents, and you also have the outliers. And this allows you to see how the intervals vary with different confidence levels. You see here that, as also mentioned in the previous talk, the higher the confidence that you want to achieve, the more you have to hedge your bets and take larger intervals. And it's precisely what happens here. And this is what you want to see. You want to see the trade-off that you have to make between confidence and intervals. The intervals might become so large that are a practical zero value, and you don't want that. So to see how this can be used for comparison and what difficulties there are in actually comparing things, I have here a chart that I took from a real life problem, again, one of cheminformatics, of predicting the potential toxicity or a metabolic clearance, in this case, of a compound that might be a candidate drug. So you can see that here, if you look at the first row, there is indeed a deviation from validity. It's not extreme, but it's there, and the two methods, KRPM and a competitive method, exhibit a different way of being somehow biased. And if you say, hold on, this guy has been banging on about validity all the time, and now we see that it's not valid. I will explain why this is. And on the bottom row, instead, you see the box plots, and you see that the method on the right has, for the same confidence level, so the same color, definitely a larger median and a much wider spread of values. And you could also see that for low value of confidence, the difference is not that much, and perhaps the method on the right might even be better than the method on the left. But these two charts allow me to make a few important points. The validity claim that I made before is theoretically backed, but under the assumption of identically independent and identical distribution of the test set and the training set. And this wasn't the case in this example. The particular study we did here wanted to evaluate how well the method could predict compounds that were considered at time, after time t, with data available up to time t. And it just happens that in particular in this domain, the compounds that you consider at a later stage depend on the compounds that you considered up to time t. For a number of reasons, because you want to explore variants of a certain compounds. You add and remove functional groups from a molecule, expecting to see, to preserve certain properties and improve others. And so you're not sampling randomly. This deviation would go away if we were to sample randomly from the overall data. When you do that, you obtain IID distribution. The second point I would like to make is that you should not evaluate, in the general case, validity and specificity independently. So here, I sort of gloated about the fact that the method on the right, KRPM, was better than the method on the left was better than the method on the right. But actually, you have to look at also the fact that for a high value of confidence, the method on the left undershoots validity, whereas the method on the right overshoots validity. So it has narrower interval but misses its validity target. It misses it by a large amount. You shouldn't. Here we have basically half the mistakes that I would be allowed to make. So you have to make a decision on what is best for you. Are you more interested in validity, or are you more interested in narrower intervals? And in the validity, the fact that there isn't a unified way of putting together the two competing estimations is a fact that is lamented. There is no solution, but I think it really depends on your application. Even if there were somebody who would say use this, I think it still depends on the application. Pretty much as in the normal case, you have a trade-off between recall and precision. Yes, you have the F1 metric, which is a harmonic mean of the two, but yeah, it's a number, but it depends really on your specific application. So here I basically state again what we just discussed. I prefer talking about once you had the chart in front of you. But again, validity guarantee rests on the IID assumption. It seems a very mild assumption, and it pervades pretty much all of machine learning, simply because it's based on the induction principle. To me, machine learning is statistics. It's based on the induction principle. If we want to have something beyond the induction principle, then we have to look at causal methods, as far as I'm concerned. But that would be a very interesting development. And there are, I know papers that look at causality for conformal prediction. But what I wanted to say here before I finish, the IID assumption can be violated very easily in practice in two different ways. If you consider that observations are generated by the joint probability of the object and the label, and this joint probability can be expressed as the product of the probability distribution of the object times the probability, a conditional probability of the label given the object, then you can see that there are two ways in which the joint probability can vary. One is when the distribution of the objects themselves varies. And this is what goes by the name of covariate shift. And then the other is the fact that the probability of y given x varies. And sometimes it's not so much the fact that we are facing a non-stationary problem, but it's the fact that in high-dimensional spaces, one visits just a small portion of the entire space. In the case that I showed you in the previous slide, I had a data set with 130,000 compounds, and each was defined by more than 100,000 features. This space cannot be visited in its entirety. Probably we're not even interested in visiting in its entirety. But my point is that in high-dimensional spaces, we visit so little in reality of the space that we have to be lucky to have a lot of regularity to make certain extrapolations or maybe interpolations, and these be valid. So when we start visiting other parts of the space, we see something that we haven't seen before, and our methods start to have problems. And again, just to finish, you should not assess validity and efficiency separately, because there is a trade-off between the two. So let me summarize the key points. Conformal predictive distributions offer a prior-free, non-parametric way to estimate the distribution of a random variable y dependent on independent variables grouped into the object x based on previous data. The conformal predictive distributions have a validity guarantee with theoretical backing under minimal assumption of test and training data being IID. So in particular, conformal predictive distributions that require only that the data be generated independently by an unknown but fixed distribution. Again, we are not making, we're not restricting this to specific types of distributions, be Gaussian or Laplacian or other forms. So we are not shoehorning reality into distributions that sometimes are justified and other times are not. And as an example, concrete example of conformal predictive distributions, which are just a framework, a concrete example is kernel-rich regression predictive machine, which uses the flexible and regularized method of kernel-rich regression to generate conformal predictive distributions. This concludes my presentation, and thanks for listening. Oh, sorry, too quick. I wanted to thank AstraZeneca for the grant that made it possible to conduct some of this research under the guidance of Professor Gammerman and Dr. Benson. And really last thing now, some references. What I presented is really, from theoretical standpoint, the work of Professor Wolk and others. And you can see here the key papers that talk about what I presented, and other sort of survey papers or papers that put things into a larger context. And now this is really the end. Thanks.
Thank you very much, Paolo. It was great, very interesting, new and insightful presentation about this new branch of conformal prediction. I do not know how much time do we have, Giovanni. Do we have 5 minutes? Because we are kind of slightly over for questions.
I thought we had another 15 minutes.
Okay.
Yeah, 15 minutes.
15 minutes. Okay, so let me open the floor for questions, please, about conformal predictive distributions.
I see Professor Campi is raising his hand. Please go ahead.
Thank you so much. I was trying to raise my hand.
Button on the list of people.
Okay.
Please go ahead.
I was trying to raise my hand with the Zoom application, but no one saw me, so I raised physically my hand.
That's for everybody. If you have.
Thanks a lot. I really enjoyed, Paolo, this presentation because it's touching a part of the story that I was not aware of. So I really appreciate being here and listening to you. So bear my question, but I'm asking just to understand an extra aspect, which is, so if I understand correctly, this method constructs regions so that the cumulative distribution function, the real cumulative distribution function, is somehow kept under control based on the empirical cumulative distribution function. So in a certain region, there is a claim that the probability is something, 10%, 15%. Now, if I understand correctly, when we speak of probability of that region, we are not talking of the coverage, but rather the mean coverage. Correct me if I'm wrong. So the mean coverage is the probabilistic coverage, and then we take average as given by the stochastic fluctuation provided by the data set. Correct? So my question is, so in the long run, if we keep repeating, basically because of the law of large numbers, we tend to. But now, say that we fixed a certain batch of data points, big N, and this is 1,000. So I don't want to repeat. My question is, are there results on top of the mean coverage somehow bounding the stochastic variability that you have in the coverage? So in other words, you construct a region and you say, okay, that region, that construction is providing me a region which corresponds to the cumulative distribution function such that before this I have 90% of the probabilistic mass. So this should be the mean coverage. Now, is there any result that is somehow keeping under control the stochastic fluctuation so that on top of the mean coverage, I have, for example, something about the variance of the coverage, the variance just to mention something. Because you were mentioning the Glivenko-Cantelli result. In Glivenko-Cantelli, you get convergence, but you also had variance shrinks so that you converge to. The question is probably not, but it would be great for me to know whether there is any result keeping under control the variance beyond the mean coverage.
Okay, I'm not entirely sure I understood the question about.
Give me a second because my loudspeaker is silent because I was using a different. I'm using two computers. So okay, sorry.
Okay, I'm not entirely sure I understood exactly the question. That one potential source of misunderstanding is the use of the term coverage, which I might be using in a different way here. I think the method that we showed bears a lot of resemblance in its approach to the frequentist approach pioneered by Neyman, for instance, for confidence intervals. So here, there was also another question that I saw from Anthony here that was talking whether what we show is conditional on X or not. And I don't know if the two questions that yours,
no,
Professor Campi,
I also had that question, but I passed on that. So it's different. So I'm not talking of conditioning on X.
Okay. Here, the coverage that we're talking about, so the validity notion that we're talking about here is in a relatively special and narrow sense. And I have been cautious in not using a notion of conditional probability. So I try to talk about, rather than probabilities, I talked about relative frequencies. Because here we are talking about the relative frequencies with which the intervals that I give, which are different for every test object, are contain the actual label. Mm-hmm. So I'm not, I was trying to understand when you were talking about coverage, if you were talking about the same thing. Here the coverage refers to the fact that all these different intervals that I obtain every time for all the different test objects, these different intervals have the property that they will contain the actual label a fraction alpha of the time, where alpha is the confidence interval, the confidence level that I decided to use to obtain the interval. So whereas you were talking about coverage, help me out here in a different way. We started talking about the variance of the coverage.
Let me follow up. So I give you data points and you construct a certain region, which is, let's say, a 90% confidence region. But the actual probability is 85 on that round.
Sorry, probability for what?
So you want to, there is a cumulative distribution function. It's there to start with. Then you have data and you construct a region. And you claim that your region.
Well, I construct the cumulative distribution for a test object based on the data. Exactly. And that is the cumulative distribution of the label.
Exactly. And then let's say that your alpha is 90%. So I give you data and you make the construction, and the real value for the cumulative distribution function turns out to be 95. Then I give you another group of data points totally independently of the first one, and the real value of the cumulative distribution function turns out to be 85. So on average is 90. So this is what they call the mean coverage. Mean coverage is 90, okay. But I would like to know whether this gap between 85 and 95, and the average is 90, can be kept under control with a finite n, a finite sample size, okay. By some means.
Okay, so I think, let me see, let me rephrase if I can your question. So let's fix the test object. We have a test object. And let's consider the case in which, because of how things are, I sample a training set. And I take the test object fix, I sample training sets, I repeat the procedure, and for this value, and for this label, value of the label, I obtain different values of the cumulative this predictive distribution. And you are asking the question, are there any studies on the variance on this cumulative distribution function? To the best of my knowledge, no, but I think we have the the world expert on the line here, so he might interject if he wants. But I don't think there is anything that I'm aware of. And I have to say, this is a relatively new development. So as I mentioned, the idea in a nutshell were sort of brought up in the 30s, but it's only recently that this came about. I'm not sure that this aspect is
That's perfectly fine.
I haven't seen any papers either on this. This is a very, very new area, right? And the validity here we're talking is sort of slightly different from the definition of validity in conformal prediction. We're kind of really looking as to how you know, our cumulative distribution function reflects the true distribution, right? So how does it vary if we kind of start to you know, repeat this experiment again? I guess this is an open question. Any other questions? We have 2 minutes.
We have questions in the chat.
Okay, we have questions in the chat. Yes. So Professor Wolfka has kindly clarified for everybody on the question regarding validity. And we have a question from Henrik. Do you suggest to use PIT as a performance metric as alternative to CRPS or as a test of validity?
In my view, PIT and CRPS look at two different things. PIT is in line with some statisticians recommend, which is called the frequential principle, which is that probability predictions should be judged only on the probability of the event that then really took place. And if you look at how the PIT works, that's what it does. However, I understand the principle. I'm not entirely sure that I agree with it, because you only see part of the story, in my opinion. The CRPS looks at the entirety of the predictive distribution. So if you have predictive distributions that are sharper and therefore more desirable, you should also see a CRPS and have the same validity as others. You should also see a lower value of CRPS. So the PIT really is for validity, and that's it. In lack of bias, and CRPS has a wider value. But again, when you then try to explain what the CRPS actually means when you make predictions, it is a relatively abstract notion.
Yes.
You know, you understand what it is, but okay, what does it quantify? Its value, what does that represent? And the integral of the quadratic discrepancy doesn't ring a bell with many practitioners.
Thank you, Paolo. I think I agree with this approach. CRPS is a more powerful technique, I think, because it incorporates the concept of efficiency as well, right? So it takes some time to understand and write code for it, but it's kind of measures more than PIT. Okay, any other questions? Okay, if there are no other questions, I would like to thank Paolo again for this very interesting
My pleasure.
I'm hopeful it was